silence, music, lights, feeling, hopefully a comfortable seat with everybody. Hey, welcome, warmly welcome to Digitalist San Francisco studio. It's a deep learning meetup, deep learning in production. Happy to have you all here, happy to see you here. I'm especially thankful for today's speakers. So we're together here actually every day sharing the space, thoughts, thinking with Valohai. Valohai AI, their machine learning platform that they are developing, and some of the bright minds of Digitalist that we create the sort of creative software, having heavy customer experience focused and a design focus with a deep tech on the machine learning, AI, and software development side. So that's what every day looks like here within our studio. And today we decided to, based on a couple of things, we thought that, hey, we're very community driven. We think that by sharing thoughts, sharing our experiences, happy to have Narendra here today to talk about his paper and ideas on the Convolutional Networks and stuff going on. So with that said, let's make it a very casual, open-minded. Feel free to ask questions, challenge, say yes if you feel like, hey, these guys have maybe figured out something that you've been thinking as well. And say, wait a second, if you want to grab more pizza or have a drink or something like that. So that's how we actually make it an evening to remember. If you feel like tweeting, if you feel like sharing some of the stuff, Valohai you can find with Valohai AI on Twitter and Facebook and Instagram, and Digitalist you'll find with #Digitalist on practically all of the social media platforms. Some practicalities, we will be having a break between each of the speaks, so that if you feel so, the men's rooms, the restrooms are on the hallway on the right-hand side when you're leaving from here. Also, if you feel like having a cigarette on the breaks, feel free to go out and come back. That's the kind of main protocol on going forward. All good with practicalities, everybody?
Yeah. Yay.
Alrighty?
Yeah.
Good. Eero, you got your shirt?
Yes.
I'm proud of you. So you're ready to take the stage?
Yes.
Alrighty, come here. And let's have an applause for the guys. Everyone.
Hello, welcome from me too. Happy to see so many people here. It's our first meetup that we're organizing in San Francisco, so I'm actually happy that this many people came up. Today, oh no, that's not it. This is it. Yeah, I'm going to be talking to you about end-to-end machine learning and some key considerations about deep learning in production. There's a few things that should be considered when taking deep learning into production, and why you should probably listen or might want to listen. I'm Eero Laaksonen from Valohai. Valohai is a deep learning platform for production. We help companies with issues that arise when you're going from just 1 or 2 data scientists to a team of 100 data scientists, or running from your own MacBook or your local small cluster to 100 or 1,000 GPUs on the cloud. We are a 2-year-old startup from Finland and now an office here in San Francisco. We're looking for customers and collaborators who have cool projects with deep learning. So that's the plug, and now we go to the actual beef. How many of you have seen this particular picture before? Okay, just a few. Okay, this is a Google research from 2015. Google looked into their internal machine learning systems and in production, and they started to check out like what's what's going on in the system? Is there something we should be considering, something we should be optimizing? And they realized that the actual machine learning code, I don't know if you can see there, but this little black box here is the actual machine learning code that goes into an in-production system for machine learning. And most of your time is actually spent on completely different things. 1 year ago, when I was in San Francisco and going to all the meetups, most meetups about deep learning were about theory of deep learning, what kind of deep networks should we use, what kind of activator functions should we use. But today, most of the talks have shifted towards pipelines, towards infrastructure, and how do we actually deploy this in practice. I've seen this picture about 100 times during the last 3 months when going into meetups and talking to potential customers for us. I think everybody who's been working with deep learning in production sort of has an intuition that says there's something wrong with this picture, that we need to fix this, we need to somehow grow the black box of machine learning and do less of the extra stuff. But what I don't see that much is the actual business why of that. So I'm going to be first talking about why I think we should optimize tools for deep learning in production, then what we could actually do to make things better, and then a little bit about concrete how we could actually fix some parts of the pipeline of going from just research to actual production systems. So, we all know it's complicated, but why optimize? The first part is money. We can save people's time, so that saves some money. But how many of you are working in a startup? Not that many. Well, what are the rest? Like large enterprises, students? What? Okay. Most companies in the Valley are not looking for savings. Most companies in the Valley are looking for something completely different, especially deep tech companies. They're looking for speed. And I think this is the key consideration, because speed also generates money, but it's very different money. It's money that comes from growth. So I argue that the most important thing why we should consider optimizing our deep learning workflows and in production pipelines is because we can grow the company and we can bring in return on investment much faster. But we can look at the savings first. I think it's a somewhat considerable part. If we look at an average data scientist salary in California region or in San Francisco region, from Glassdoor I found this number, $165,123 yearly salary. That's the base salary. I think that's a nice amount of money for playing around with Jupyter notebooks. But if we can save these people's time 1 or 2 hours, if it's just one person, it's going to be about 20,000 a year. If it's 2 hours, we can save 40,000. And then if the green team grows, we can get to a huge amount of 400,030. So for a San Francisco company, will this be enough to push the needle? Is this something that's actually relevant? Maybe it's starting to be around that ballpark that it's actually considerable, but it's still a small part of what's going on. I think that speed is the thing that we should focus on here. But we have to define what is speed for deep learning. And I argue that it's who deploys return on investment first. If you're doing deep learning, unless you're doing it in a research facility somewhere in a university, it's probably someone wants you to build something that will generate value at some point. Am I right? Does someone have another opinion? Everybody's silent, okay. Somebody's smiling? Maybe, yeah. So, if we just look at how we could get to the goal faster, I think that one considerable part of deep learning is experimentation and iteration of models. So if we just look at 3 different teams that work at different paces, I think this is pretty self-explanatory, but when you go and actually talk to teams that are doing deep learning and trying to achieve something business-wise, they haven't thought about this too much. But if the amount of experiments is the thing that you have to go through, if we have 3 teams, one working at 1x, a second one working at 2x the speed of the other one, and then a third one working at 3x, and then we consider that maybe these teams have like 1 person, 2 person, 3 person, so they can't work with 100% capacity, but maybe 80% because people actually have to talk to each other and share information, which is why. But anyways, we get like 3 different, let's say it's a startup. We get a startup that finishes a product in 12 months, the second one in 7, and the third one in 4 months. You've probably been a while in the valley, or at least you're going to be. So if you make a product in 4 months compared to 12 months, like the third one is never going to even see the light of day. Like that's forever. That's forever in deep tech right now. So if we can actually achieve these kinds of improvement, it's going to be very considerable from a business perspective. Then a few factors that actually affect this. So we can look at how long the actual experiment takes. You know that if you're doing deep learning, your experiments might take from like 15 minutes to 6 weeks. Does anyone have a really long experiment they've done? How long have you guys been running? Anyone?
8 hours.
8 hours? That's still like, that's a long time, but...
5 days. Yeah, 5 days.
5 days, yeah, that's getting there. Very efficient use of work. Like, I would love to play like Tetris for 5 days and wait for my experiments to run. Probably don't make my CTO or CFO very happy, but I would love to do. Then, how many experiments can we run at the same time? Then, how many sensible things we can come up with. So it's not just the amount of experiments. If we can make an infinite amount of experiments, we probably can't just come up with the new things that we actually want to try out. So we need to do that. And then we're going to need to be able to assess some of those results and have feedback from that. So how might we approach this? Our team comes from software engineering background. We've been working for several, like maybe about 15 years in all of our team in like really state-of-the-art software development environments, how to deploy software really fast. So I'm gonna give you a few examples of things that happen in the software world and that we think can be used as role models to think about deep learning in a more productive way. First thing I'm going to mention is access to infrastructure. So if we think years back, infrastructure was very different. Today, it's like this. You go to AWS, insert mom's credit card, and you can run a cluster on a global scale. That's it. When we look back, it was like, let's dig a hole in the ground, and then maybe 2 years later, we can start shipping in some computers. So a huge difference in like what scale we can develop with a small team. Then another thing, if we look at software development in 1998, was anybody around? Do you remember this time?
I do.
Do you remember this time do you remember when we deployed 4 times a year and everything broke? Yeah. Well, how many times does Facebook deploy a day? Like, I think 10 times a day is a small number, but that's like an average for a web company. That's a medium-sized company. These guys are deploying 10 times a day to production and breaking nothing. Well, every now and then they break something, but most of the time nothing breaks down. So what happened in between? Does anybody have any ideas? GitHub, yeah, version control, for sure. I'm going to argue that continuous integration as a process happened in steps and so on, but the approach of a standardized workflow, how to go from a new pull request to actual deployment, doing testing in between, trying out everything, unit tests, and just a standard workflow is definitely one thing. And then third big thing that I think we should look at in this context is microservices. So now we have split our system into small parts. How many of you are familiar with microservice architecture approach? Not everybody. So yeah, so we split our software into parts that work over an API. So individual teams can iterate really fast inside that microservice, and as long as the API doesn't change, you don't have to think about anything else. You can just iterate really fast on these small portions of the application. So you can have all of a sudden 400 teams that are deploying every day many times without having to think about what we break and who we should contact to before we do this change. All right, so how does that tie into deep learning? I'm gonna look at 3 different aspects. First of all, hardware, how we should think about hardware with deep learning. Then software, and thirdly, teams, how your team can work better, how you can scale your team. First, access to hardware. We have been doing a lot of benchmarking on different systems. Looks like I have an old set of slides here for some reason, but doesn't matter. If we have P2 and P3 instances on AWS, are you guys familiar with these instance types? So if we just look at sheer power, it's about 5x. This is SHA computations, like SHA 512, some sort of benchmark. Doesn't completely translate to deep learning, but anyways, it's about 5x. The price currently is about 1.7x, and then if we look at a real-world TensorFlow example, this I think actually is 3x if you think about it, not 4x. But we can go from like 1 hour to 15 minutes for a training run. So if you're using old hardware instead of the newest stuff, you're essentially paying a lot of money, but you're also making your data scientists sit on their hands waiting for stuff to run and paying a load of money just to have them there without them being able to do anything. So not just the amount that you save for the hardware, but also the amount you save for having your people, and then of course increasing the speed, the amount of iterations you can make on your model. Then distribution of hardware. You should consider that if you have this set of, be it on-premise hardware or cloud hardware at your disposal, how do you give it to your people? It should be completely trivial to use. Nobody should have to request for instances set up for them or something like this. It should be, you should have it like this. When you have a new version of code you want to run, new training job you want to do, it should be just one click of a button and it should be running. Then it should be optimally utilized by the team. So we are not very big fans of virtual machines. So a very common approach is set up a big EC2 instance and SSH in and do your stuff there, or set up a Jupyter notebooks on that machine and just run there. And then when you go home for the weekend, just close your laptop and forget the instance on and pay for the machine running that's actually not doing anything. That's a very common approach. But that's not very beneficial. It should be more queues. So if you have a team, everybody should be able to send their jobs to a queue, and then automatically those jobs should be computed by machines that have relevant hardware for that particular job, and just get it done. So you're distributing the whole hardware capacity that you actually have to your team very efficiently. So get in fast, deploy your code, run the code, get the results, and shut the machine down, or give it to someone else. And then thirdly, a very managerial perspective. You should have very transparent access to cost and be able to control cost. So if you do a training run, you should be able to understand what does this cost for a company, and also management should be able to understand what's our cost for this month and how is our cost being projected for future. Has anybody had any issues with this, with management? I'm presuming most of you are. We can actually have a quick sort of show of hands. How many of you are data scientists? All right, most of the bunch. How many are more engineering people? Developers? Okay, that's sort of the rest of the half. That's a good split. Oh, awesome. And then, do we have some management or?
I'm the guy with the cost.
All right, and then what else? Is there someone who wants to say something? I am this. No. No one else has the guts to open up. All right. Cool. Then, when we go to actual large systems, parallelization becomes a really big thing. How many of you have had to do some sort of parallelization with deep learning code? So still, there are some people. There's three main things for parallelization. All of them should be built completely trivial. First is hyperparameter sweeps. This parallelizes very nicely. All of the stuff that you're running should be completely isolated packages that you can just run in parallel. Don't have those like nested for loops that are going linearly through stuff and waiting for 6 months for that to go through. You should distribute that on different machines and run. Does that make sense? Some of you are like, yeah, that's awesome. And that shouldn't be a huge job for someone to do. Let's say you want to go through 1,000 parameters. That's just a list of parameters that you give, and then go ahead and calculate. It shouldn't be something that you set up some server that takes your stuff, or set up 10 Amazon instances and then figure out how to distribute this stuff and gather your results and so on. It should be a tooling issue that should be handled by someone else other than the data scientist. And it should be a tool that's available in your company if you want to do real in-production machine learning. Deep learning. Then data parallelization. If you're dealing with huge data sets, you should be able to do data parallelization pretty trivially. There's great tooling out there now. There's sort of two levels of this. Single node data parallelization. So if like 8 GPUs is enough, then usually you can just work out with one machine, and most tools like TensorFlow support data parallelization out of the box if you're working within a single node. Then again, if you're working over multi-node that's connected via network, it becomes a little bit more complicated. A good approach for that is Horovod. Has anybody worked with Horovod before? Has anybody done any data parallelization? Okay, so when you run into this, so let's say you have a terabyte of data, your training run takes 6 weeks, you want to optimize that, you can split your data into chunks, you can distribute it on 6 or 10 different machines, and then each of those machines will train on a small set of data, and then they will share the gradients between those machines. And there's great tooling available for that, but it's a little bit complicated to set up if you have to do it from the get-go every time. So this should also be available out of the box for your team if you want to do larger data sets. So just like, I'm gonna wanna train my model with this data set, this amount of machines, and then should just work. If you do it from the get-go, I'm sure we're gonna hear something about how fun it is to configure these things if you have to do it yourself. But if you can provide tooling for that for data scientists, then that's a really great thing to do. Then model parallelization, which is the most complicated out of these. There's no available out-of-the-box tooling how to do this. You just have to build it from the get-go. So this is if your model is so big that it doesn't fit in a single GPU memory. And that's a little bit more complicated issue to solve. Not so common nowadays anymore, since GPUs have quite a lot of memory and most models need to actually run somewhere. So we tend to optimize the models a little bit so that they are not like 200 gigabytes a model. But there are use cases where this is also, we're gonna hear about that. All right, that's it for parallelization. Then software. I would strongly recommend people to use existing frameworks and existing tooling. Just even if you were able to build this obscure implementation of some deep learning network on C++ yourself, it's probably not going to be fun for the next intern joining your team. It's probably not going to be very fast to scale your product and team if you built everything out completely custom. So this is the same thing as for software development. Please use existing open source tools just because it's going to be so much faster to scale. And at some point, the 100 or 300 man open source plus Google team is probably going to surpass your implementation anyways. And that 2% just doesn't matter because you can throw more hardware at it. Then package management. So you should be able to manage, have out-of-the-box package management for your models and pipeline. This means that when you're doing some software, you should always know what version of TensorFlow, what version of CUDA drivers do I need for this particular machine. Containers are a great tool for doing this. Most companies that we see building pipelines actually use containers to do this. It's a good approach. Then next is a team. So how can we optimize building and scaling your team? Sharing of work is one thing. Always think about how, when you're doing some experiment, running something, how am I able to share this with my colleagues? How will my colleagues know what I did 6 months ago? First thing, reproducibility. If someone wants to take your model and run it on a new set of data, they should be able to do that with one click. Not spend 2 weeks installing all sorts of thingies and thinking about how to actually run this and where did my data come from and what version of data was it. Secondly, record keeping. Have a good understanding of the history of what's been done. Let's say one from your team leaves. You might want to actually know what that guy was doing for 6 months. We have a lot of customers coming in who were, we meet them with 1 year ago and they're like, no, we're good. We're using Google Sheets and I'm sure our data scientists are putting stuff in. And then they call 6 months later, like, oh, our head of data left. We have no idea what we've been doing for the past 6 months. So that's a lot of money down the drain. So you should have automatic record keeping. You shouldn't have to think about how, you shouldn't have to do manual work to know what version of data, what version of code was used for this particular model. And then lastly, pipeline documentation. So when we talk about deep learning, it's not actually just one version of code and one version of data that's going through. It's a pipeline of code and data. You have first your data, and then you have feature extraction code that does something to your data and comes up with features. So now you already have one version of code and one version of data you should be able to match to come up with this particular set of features. And then you're probably going to be training a model, and you're rarely training just one model. You have 6 competing models. You have different people working on those models, but maybe using the same features. You should be able to understand the whole pipeline and then going from there to deployment. All right. I actually, for some reason, have a wrong file here. Just a sec, I will take one more slide. Yes. So the last thing I talk about before stopping is cake and data entanglement. So this is one of the things that I think are fundamentally different between software development and deep learning, or actually machine learning in general, that makes this so much more difficult than that software development is. So we already talked about this pipeline where data and the code work together, and we should have versioning. But the core issue here is that behavior is affected by data. In software development, behavior is only affected by code. But in deep learning and machine learning, just in general, your behavior is affected by a combination of data and code. So you should have equal versioning and equal testing for both data and code, and be able to understand that pipeline throughout. So that's where the deep learning pipeline comes into play. Then, one more thing, deployment. Are you guys deploying models? This is a huge subject, deploying deep learning models, very, very complicated. I'm just gonna give a few things to consider. We're huge advocates of microservices in this thing. You should first of all have a different testing environment and a different production environment, so you can work just like software developers do. They develop and deploy the testing before actual production. Then you should be able to run tests for that particular testing environment. So if you're doing some sort of software and deep learning is just a part of it, it should plug into your existing CI pipeline. And you should be able to run the CI pipeline before taking deep learning into production. Then testing with real-time results. So you should be able to test, if you're doing real-time predictions, you should be able to test with real time. And thirdly, the microservices, you should have, if you're a data scientist, you should have complete ownership of your models. You shouldn't have to go to a DevOps team to ask to deploy a new model to testing or production. This will slow your process down very, very much. So think for ways how to build the environment so that data scientists can actually deploy their models without having to go to another team and ask and beg for time to deploy something or set up servers and so on. The tools, for instance, that we provide give you a possibility to just one-click deploy to a scalable Kubernetes cluster to an HTTP REST endpoint that you can then give to the people who are actually using your models for production, and you don't have to think about anything in between. So this kind of approach lets you so much, it gives you so much leverage for iteration and deploying faster. So in ideal world, you should be able to run a distributed training run on n GPUs with just one click. All of these things, just one click. Think about how you could approach your pipeline so that you don't have to do any extra work to do these things. Every run should have complete reproducibility. Have all records kept. You should always know the environment, the data, and the code versioning that you actually run. Get real-time results from your execution without having to go to that machine and get those results. You should somehow be able to have them. Run automatic testing and deploy to production with just one click. And then you're in pretty much an ideal spot for building in production tooling. So making this look more like this. All right, thank you. Any questions?
Can you really do it all with your platform?
Well,
was this the kind of a promise?
Well, no. So these are the things that our company tackles. We do a lot of this stuff. We optimize a lot of this stuff. Some of it's still vision. Some of it is still in pipeline. But most of it, yes, we can help with. And of course, it depends a lot on your use case. Like if you're using the companies that have to use on-premise hardware. There's companies that, like for instance, I was talking about microservices. What about if you deploy to a Raspberry Pi? Deployments can be very different, but most use cases today are still online. Of course, like on-premise deployment is growing all the time, and that makes things very, very complicated. There's also standardization happening there, but it's still years away. Anything else? Yep.
Can we see your UI, or are there privacy concerns?
So if somebody wants to talk more about like how we approach this issue and how we do stuff, you can grab me and talk to me, and we can organize a demo or whatever. That is possible. But I'm not gonna spend your time by.
Don't we get a product demo?
By demoing our product.
And it's online. You can also see a lot of that in the website and all that. Okay?
All right. Thank you.
Cool. Thank you, Eero. Good. For the people online and for all of us here, if we are we good today? Are we sharp as well? Can we manage a 5-minute break?
Yeah.
Okay, cool. Then we do the 5-minute break before Mikael and Kyle will step in from Digitalist and talk more about deep learning with the graphical image processing. So 5 minutes, and then we'll continue. Stay tuned.
Kun sä ajattelit. Oh. Terkkuja striimiin kaikille.
Alrighty. Cool. Cool. Good guy. Alrighty, take your seats. We'll go on with the next topic of today. We have a couple of very interesting cases ongoing with the imaging part and utilizing some of the models, and that's why I'm happy to have like Kyle here, all the way up from North Vancouver, and our team and ML team from there, and Mikael here from our San Francisco studio. Very big thing within Digitalist that we're leading and believing on the culture is about sharing the experiences, thinking about you know, if we've come up with something, we'll give it up back to the community, both online, streaming, in the meetup events, and so on. Just telling where we're heading, and grabbing one of those kind of ideas and things from there. Feel free, once again, thank you for all the questions this far. Anyone over the line, you know, feel free to drop them. We'll have people actually watching over on it. And with that said, Mikael, Kyle, welcome. Yeah. And an applause, a big hand, how to say.
That's a quick intro. I'm Kyle Hounslow. This is Mikael Laine, as Stefan said. We're machine learning engineers here at Digitalist. We work on a broad range of projects, ranging from like some NLP stuff, creating chatbots. There's like also like anomaly detection in the power grid and some heavy-duty machinery for like preventative maintenance and automated alerts and stuff. But today, talking about a very fascinating project in computer vision. Like, really happy to be working on this one, where we're generating stereoscopic 3D imagery from just 2D imagery. So given a left image, what's the right image? For left eye, right eye. And so Mikael will be going over some like model architecture and how the stuff kind of works, show some demos, and I'll address some of the engineering challenges that we've faced thus far dealing with high resolution imagery. Just noteworthy is that it's not a case where speed is really our client's concern. It's more output quality. So like when you're dealing with 1080p images all the way up to 8K, and output quality is of the main concern, kind of run into some issues. So I will leave it to Mikael to start us off. Hope you enjoy.
All right, thank you, Kyle. And again, remember, you can ask questions anytime. So let's start with the basics. Stereo images consist of two frames. And if you have some sort of VR goggles, you may have seen these. The idea is that items that show up closer to you are shifted. So if you're looking at your finger with your left eye, you see it in this direction. If you look at it with your right, like this, it's shifted left. So objects that are closer appear shifted in the other frame. Of course, there's a lot of content that doesn't have the other frame. And that's kind of a problem, kind of a letdown for if you want to have some cool content coming through your goggles. And we have been experimenting with using this encoder-decoder fully convolutional network to try to guess what the right frame might be from the left frame. So we have convolutional layers, scaling down convolutional layers, you know the encoder-decoder network architecture. Some of you. And we also have these skip connections in there, so it's more of a unit architecture. Maintaining some of those high-resolution features for later. So that's the basic system, and we kind of approach this a little bit skeptically, like, does this even work? So we started feeding some pictures in it, taking a left and right image, a small batch of images, and sure enough, as you start running it, first of all, the network doesn't know anything about depth or anything, but given the ground truth, it starts slowly through experimentation, of course, and I mean the randomness of the kernels, and then feeding the error back, learning how to distinguish from various features in the image the actual depth, and eventually it produces some nice convolution kernels in there in the bottom right as well. That kind of give you an idea of the kinds of features that it's looking for when it's trying to decide if this object is close or far away. So that starts looking pretty good, actually. So how exactly does it work? Well, we don't know for sure. I mean, it's all inside that big network. It's a pretty huge network, and I was going to talk about how that's really a huge problem, actually, the memory footprint and everything. But some of the things are clear, like sharp edges and things of that sort typically appear in the foreground. So out of these kernels, we can point out some that the activations look kind of interesting. So like this one, for example, will detect these edges, slanted edges, and there you see the activation for the first layer, first convolutional layer, where the features come into the network. So that sharpness of edges, also from optical effects, when something is out of focus, that's typically on a different depth level. But this is something that kind of generalizes to real life. I mean, objects that are far away appear to be kind of blurrier in general, just because the scale is lost. Like, there's probably a mountain down there, and it's probably kind of a spiky mountain. You can cut yourself on it, but here it shows up as this blurry oval shape. The scale features, that's kind of obvious. If there's a man in the foreground, he looks bigger than the man in the background, and the network can learn stuff like that. And one of the things that we actually have control over as we're choosing how to deal with the colors of the image is hue and saturation of colors. So if you've gone hiking, you probably know that far away objects tend to be blue. So you have trees in the foreground that are green, and the further away they go, because of the atmosphere, they turn kind of gray and blue. But also because of just the optics of whatever image sensor you have the diffusion of light. So even in a picture like this, where there isn't much atmosphere between back there and here, you see that the saturation goes way down, just because the image sensor is saturating and the optics. So saturation actually ends up being a pretty good measure of distance. And we've been experimenting with 3 different color spaces. The YCC color space, which is kind of geared towards and designed for the way the human vision system works. The human vision system, of course, emphasizes brightness and contrast. Chroma, the color aspects are not that important. RGB, an obvious choice. From the point of view of deep learning, you could say that the network should just learn So colors that kind of vanish into the background because of the atmosphere or optical effects or image sensors can be taken into account. And also brightness, which, you know, biological vision systems are geared towards. So take the saturation and value instead of the RGB. Don't know why that's that was. And we find that the differences are actually very small. So even though we have 2 channels instead of 3, everything we've seen so far seems to indicate that we're doing just as well, and sometimes actually better than with RGB, especially if you have a lot of colors. We used to have some problems with some data sets with the color red, for example. It would always get brought to the foreground, even if it was actually in the background. Or if you have football scenes where the green grass is in the background, then the guy with the green shirt shows up, and he gets, or part of him gets dragged into the background, which is a problem. So with HSV, we end up emphasizing spatial frequency domain features, like we talked about. So now, as for generating the image itself, we have a couple of options that we've tried. And one is simply, let's use the network as is, put the left image in, and compare it to the right image, and have it reconstruct the image. First, encode it into these abstract features, and then reconstruct it. And that works. It's fast, and it's actually kind of magical to see that work. Looks kind of like the animation I showed before. And for our first test, that was great, except one of our requirements is we have to have control over parallax. That ended up being a problem. The other is that the reconstruction of these images is imperfect, so the output is blurry. And to remedy this, we are now ending up using a disparity map. So we actually generate kind of the depth, kind of close to disparity. Disparity and depth maps are kind of related. And from that disparity map, we then do the actual rendering of the final output image. And this gives us a lot more control over things. We get the results of our depth segmentation explicitly, and we know what they are and control them. So the parallax control works kind of naturally. And the output pixels are off from the original image, so we don't have that blurring effect. As a side note, when we started looking at the first type of network, one up here, we still needed to do parallax control. And so we looked at the kernels. We took the average of all the kernels in the whole network and found that they were slanted towards the right, like this. And when you look at the horizontal situation, it's kind of obvious, right? We're taking pixels from the right and pulling them to the left on average. So you can kind of do parallax control, and maybe someone will find this useful for other projects. It's kind of hardcore. You actually go in the network and you modify the final effective kernels by taking a weighted average between the kernel and this single value kernel. Couldn't find a name for this, by the way. But a matrix, matrix in this case, with just one value in the middle, which is the average of the values in the original kernel. And then with P would be the parallax setting. So P being 1, we would do full parallax, take advantage of the network's power. And P being smaller, we use less and less of that and let the image true as is more and more. And it kind of worked. So this is one of the early tests, low res, but still. And so there you have the maximum parallax. So this again is the left image that we're given. We're trying to construct this with different parallax. So yeah, we kind of were able to do it. But of course, using the disparity map eventually was so much easier. we simply multiply the disparity map by a coefficient, and rendering network generates corresponding shift image. Another kind of cool example here. And you'll notice, so one of the things in generating the other images, when you shift one of these objects to the left, we don't know what's supposed to be revealed underneath. But here, since the background is grass, it doesn't really matter. It's all the same green, kind of generic green stuff. Another one, some maybe a flag. Stuff like this. So that's all I have, and Clyde will come up and explain how the infrastructure for this project actually comes to be. Thank you. Any questions at this point?
Oh, we can get some questions out. No, feel free to interrupt me at any point. Thanks, Mikael. That's pretty cool. I kind of want to go back to this. Yeah, so like, just to reiterate what's kind of going on here, if you ever worn VR goggles, this is kind of like the amount things are coming at you. So if you were wearing goggles, the paddle would be coming towards you and back. That's kind of the parallax control that our clients have here. So we're talking about some of the engineering challenges. Like I said, dealing with high resolution imagery, you can see some of that was pretty low res because some of the stuff that we're doing right now is more experimental. We're trying to just get proof of concept like that control over parallax, etc. And we need to scale out our training pipeline big time to be able to accommodate high resolution imagery. And so one of the first ones is pretty obvious, is like storage space. Where do you store all this stuff? I mean, like, just put in perspective, even a pretty high compressed 8K video is like 200 gigabytes per hour. It's got like hundreds of videos that you have to train on. Still a lot of stuff to store. And so the model ends up taking a long time to train, especially when you increase your data set size from, like, let's say you start with 15,000 and you go to 150,000, 1.5 million. Like, it doesn't scale linearly. It just kind of blows up. And so you more training steps per epic, and the larger the images, the longer it takes to feed through the network. And so sometimes even computations are too large to fit on a single device. If you have the whole model, it's pretty easy to understand. But even like, let's just say one of our convolutional layers with 64 kernels, so it convolves 64 times, it generates roughly 8.5 gigabytes of activations for an 8K image. So like, let's just say like a Tesla V100, it's like 16 gigabytes, right? It's like two of your layers could fit on one of those devices, which is pretty crazy. And we have 8 of those full resolution convolutional layers. It's hard to say the words like it's not possible, but maybe we might be getting into that area soon, but I'm not sure. So our requirements for storage is that we like to have a central repository. So like reproducibility is really important when doing these experiments. We want everybody to have access to the same data set and be able to contribute to that data set to build it up. It could be potentially hundreds of terabytes in size. We haven't gotten there yet, but it could be. And just be remotely accessible from your local machine and any cloud instances that you spawn up. And so we found that Google Cloud Storage or Amazon S3 are both good choices, mostly because they're supported by TensorFlow's file.io. So if you want to like load in new checkpoints or feed in imagery that's kind of abstracted away from you, you just put in the bucket URL and it'll load up whatever file you give it. Also, like, I'm not saying that remotely accessible NAS at your office or something isn't useful as well. There's just some overhead required to set that up and maintain it. So just a couple tips for cloud storage that we found so far is if you use the same vendor for your compute instances as well as your storage, there's no charge, like network fees between transferring the images back and forth to kind of give you that bonus. Also, it's good to choose the same region for your compute instances as well as your cloud storage, so there's less latency going across the US. And try to choose the regions close to your office as well. If you're going to be transferring files there and back, it's a good idea to do so. This is like a typical storage setup. So you have your local machine should have access to talk a bit about distributed training, some of the challenges we face, some of the successes we've had, and why we might get to know Valohai a little better over the next month or two. Is there are two types of distribution strategies. Eero kind of went over them a little bit there, but just to reiterate, data parallel, split the model across n devices, and theoretically you should be able to train n times faster because you're splitting the data up. Another one is model parallel. So you distribute the model across n devices to be able to accommodate, let's just say, n times larger models or input data. So for data parallelism, when you use it, well, the model needs to be able to fit on a single device if you want to replicate it across devices. And it's probably, if you only have like 1,000 images, you probably don't need to parallelize it. You just run it on one device. But if your data set's large, it's a really good idea to do this. And so TensorFlow has a couple built-ins. Just over the summer here in 2018, they came up with mirrored strategy. It's not a completely new concept, but it's built into TensorFlow now. You just instantiate a mirrored strategy. There's also parameter server, and it's Orgot. I mean, that's if you want to go multi-node, not just on one device. Just to mention, like, this only works on one machine with n GPUs. You can't go cross-node. And so let's go through an example. So this is non-parallel. So let's just say you just put it on one device, feed through your training batch, you compute the loss, and do back propagation and update your parameters. That's just first single device. And so we're going to be doing data parallel. In this example, it's ring all reduce. So you feed in batches divided by the number of devices. You perform back propagation individually on each device. And then use the ring all reduce algorithm to update the parameters across all of the devices. So it's kind of, you get the same result, you get 4 times faster in this case. There's a busy diagram at the end of it. And so if you want to do TensorFlow, I mean, like, if you've heard anybody use like the estimator API with TensorFlow, or people use Keras or PyTorch, what's popular here? Not sure. Okay, well, one of the popular TensorFlow APIs is estimator. So you just create this estimator object and you just call train and evaluate, and it'll train with the trained data, evaluate with your evaluation data, and you just need to add like a couple more lines up here saying like how many GPUs you want to mirror across. One of the things just giving TensorFlow permission to choose the GPU, and yeah, then you just set up that config and pass it into your already existing estimator. Yeah, it's quick note. So like once you start doing data parallelism, like the bottleneck is no longer your data actually going through your network in most cases. It actually starts to become the computations that you do on a CPU, like pre-processing your data and even like loading it, like I'm talking about cloud storage, transferring the data from the cloud to whatever VM that it's on. So you, like while your GPU is computing those gradients and all that, you need to be at least using your CPU during that time. So you need to have some parallelism there. And you know, people at Google thought of this, and there's a dataset API. You can like pre-fetch. This is the API called .prefetch, and you can like load in your batch while the rest of it is computing. So that's really useful. We found like significant speedups actually by like 4 times by switching to the dataset API. Okay, so model parallelism. So as Eero mentioned, there's no like real like standard way to do this. You kind of gotta build it into your code. You can't just like call mirrored strategy. You gotta like actually think about which layers of the model you want to compute on which device. And it doesn't. It's not so obvious at first. And so you use this when large model cannot fit on a single GPU, and yeah, like the computations. So like we have a fully convolutional network, so it's not the model that doesn't fit on the device. It's actually like when you, because it's kind of the input can be scale invariant because it's fully convolutional. So if you increase your data input size, that's when like the activations actually blow it up, like what I showed before with the 8.5 gigs. So how you do it is you assign the parameters and the convolutional layers to different devices, and you need to have full control over that yourself. You need to make the decision by yourself. And so here's an example of our network. So just before I start, like the bulk of the computations are here because it's still at full resolution. So when you're convolving across the full resolution before it starts getting downscaled into the encoded version, that's when the activations are so large, right? So you need to think about it. You don't just go like split it into 4 parts. You gotta actually think about it. And I tried this and it actually helped. Was that you put the first GPU on the larger first initial convolutional layers, kind of the middle part on another GPU, and a third GPU on the final layers of the decoder network. And then we have this extra rendering network, which actually takes up a lot of memory as well. And we put that on another GPU to be able to forward these super high resolution imagery through the network. And so here's a quick example. So yeah, most of the neural network libraries kind of look the same. So like let's see, define a bunch of layers in TensorFlow. So we actually have to do in that model function is specify which device you want each layers to reside on. And so like just quick note that these in TensorFlow you can actually put like a network address. So you can see like I want this one to be on like machine 1, GPU 1, and all that stuff. Like that's getting crazy. I mean like you know some kind of management tool for that. Hopefully Valohai can probably do that. But yeah, getting complicated there. So this is my last slide, and just a quick note. We found that containerization has just been huge for us. Does anybody here use Docker or containerized stuff? Yeah? Cool, yeah. And so it's just like when you're using GPUs and stuff, I don't know if you guys have seen this. I see this like all the time. It's like you upgrade from TensorFlow 1.8.1 to 1.8.2, and they've like changed their QDNN library. It's like, oh, I can't find this and that. So like, so being able to just like to know that your container is going to work in the cloud is always good. And so I've seen that error all the time. And you can leverage out-of-the-box scalability of a third-party training platform. Yeah, I'm plugging Valohai a lot here. Jeez. I really like this stuff. It's like, it works, I'm telling you. And that's it. Yeah, if anybody has any questions or anything, I'm glad to, no one interrupted, so.
So thank you, Paul. Thank you, Kyle. Thank you, Mikael. I find it interesting. We go forward, so have a little break. Sure. Before we unwrap, if there's any questions during the break, anything that raise your interest, know that Mikael and Eero are here just for that reason. So we shoot for another 5 minutes sharp. I think we're good. So let's do that 5 minutes sharp, and then we'll continue with Narendra after that. That's our last speak for the beginning. Good.
Yep.
A big hand.
I
Yes.
have a question. About the scalability, the model is very huge. How it updates across the domain, like from one GPU to GPU1, running the model itself.
Yeah. And so like TensorFlow, that's the thing with TensorFlow is
I see, okay.
Yeah, I know, I thought I was skeptical about that too, and then I just did it, just work. I'm like, okay.
Yeah, otherwise there would be like, you have to schedule everything.
Exactly.
Wait for
I know.
one to finish and then update it.
I thought the same thing. I like lost sleep over that. I'm like, I don't even want to try this tomorrow. But yeah, it works.
Okay. Yeah, thank you. And what is the concept behind the usage?
Like for the actual application? Yeah. So like in VR, like a lot of content's coming out. That is oh my god, here. I'm at the football game, at the soccer game, whatever, right? I mean, that's stereoscopic imagery. And I didn't know this before I started the project, but there's like a lot of manual work that goes into that. People actually have to come like map pixels from one to the other and generate that. I didn't know that either, right? Yeah, so it was a big need for people to like help generate imagery from these. At least in like rough or close. That's like a really hot commodity too. But I'll just estimate what it's
One last question. I actually pointed out that it's somewhat doing shadows. So you are repeating the feature there where it activates the shadow function also because when you're in light and you're
Where you parallelize the model
last one to go. Not definitely the least one. So feel free to grab a drink, something to eat still, and then we're getting ready for Narendra Patwardhan. I think I got the name right. I mean, some of the people here today have Finnish names. They're not easy themselves either. But I have to say, I kind of took a couple of looks with Narendra. Glad to have you here today. Really, I'll let you introduce yourself. And I read your paper online on a little bit touching on what you're going to be talking, and it's time to hear it. Perfect.
Sure. Hello everyone, my name is Narendra Patwardhan, and if you cannot pronounce it, you can ask me later on yourself. So, I'm a researcher at Michigan Technological University. I'm a graduate student there, and I'm also working at a company called DeepKappa, where we develop AutoML algorithms. So today I'm here to talk about my paper regarding a novel activation function, which is called Adaptive Richards Curve Weighted Activation, or ARiA, and how you can add 3 to 5% of efficiency or whatever n metric that you can care about in just using something like 3 or 4 lines. So this is what my presentation is going to be about. But first, we need to understand what is the need for research in production at all. So the beauty of deep learning is that the deep learning models allow for easy transference of knowledge, not across just a single task, but across different tasks with different data sets as well. You can just grab a model that is trained on ImageNet, just swap or replace the couple of last layers, and you have to train for something like a couple of approaches, and you have something that works 95 to 99% of the time. Then why do you need to do research at all if it all works? Because if you can do it, so can 10 of others. And since we are in Silicon Valley, I bet that number is quite larger here. One of the great advantages of deep learning is you can tailor your model or your system to what you want it to have. CNNs are kind of like new thing recently, but till UNIX came, there wasn't much that could be done for image segmentation. Going back a couple of years, DNNs were good, but till CNN came, image recognition wasn't as good. So if you tailor your model to what you want it to do, you have a definite increase in accuracy. And if you want to pull the last bit of accuracy or have a competitive edge over the other competitors, then you have to do research. So my talk is a little bit more fundamental. Why do neural networks work so well? Well, they are universal theorem, universal approximators. But what's the difference between them and any regular regression talks, like linear regression or logistic regression? Is neural network just stacked blocks of linear or logistic regression? Well, the answer is definitely no. Neural networks distinguish themselves from all the other branches of machine learning in one thing: they have inherent nonlinearity. All the processes in the nature are inherently nonlinear, and that's why neural networks can provide a good approximation. Just remove the activation function part, and what you have is stacked layers of linear combination of weights and linear combination of weights again. And that's not a good approximation of any realistic system. You have to have some kind of nonlinearity added to your system. So, what were some of the traditional activation functions that were used before? Since the start of deep learning started with the Hounslow function, after that we switched to sigmoid function, and after that we switched to tag. If you look at these functions, you can see that they are going from simpler to something more complex or something more continuous. Now these functions work well, but what's the drawback in them? If you can see, they saturate at their extremities, and that's the problem that we term as vanishing gradients. other, while backpropagating the loss, each weight is not having as much of effect as it should. And if you compound that effect going backwards, each effect is getting diminished again and again. And that results in something that could not be computed because it's extremely small. So we end up getting NaN values. So NaN is kind of like the most famous error that we have besides the TensorFlow's CUDNN not found. So yeah, NaN is not a number, by the way, just for those who don't know. So vanishing gradients pose a lot of problems especially for image recognition tasks, because your approximation capacity increases with number of layers that you have till a certain point, of course. And then comes ReLU. ReLU is the cheapest activation function that there is, and that's why it's more famous. Why is it the cheapest? Because it's computationally cheap to calculate the gradient of ReLU and the forward function of ReLU. You may think that this function is not nonlinear because it's a combination of two linear functions, but that's how ReLU family works. Combined together, it's a non-linearity. So one of the key advantages is it's just a combination of 0 below 0 and x above x, or 0. So ReLU solves the vanishing gradient problem because it has no upper bound. So it continues to increase further and further. So in a way that it doesn't saturate. And if it doesn't saturate, then that means that it doesn't give vanishing gradients. But with that came another problem, that is exploding gradients. That's the exact opposite of vanishing gradients. It has no upper bound, it continues to increase and further across the layers, and then you can calculate it because there is also an upper bound on what value you can calculate. So we end up getting infinity on NaN. So the more fundamental problem with ReLU is because it has the definition 0 below 0, and that's a constant. That means that if the weights update end up being such that it gives some negative value in total, then it may never recover from that point. It ends up giving no value from that point onwards. And if you think about it, more than 30% of neurons in your neural network, if you use ReLU, end up doing nothing. And that's called the dying neuron problem. So, yeah, it's one of the most used activation functions. So, are there more sophisticated activation functions? There are. And even though this slide is about Swish, I would like to introduce a couple of few other activations first. There is a parameterized ReLU, or PReLU, which just changes the slope of the positive part of ReLU. There is LU, or exponential linear unit, which substitutes the negative part of ReLU with an exponential curve. And then Google found out that we need to do something more to find an activation function that works well. And they solved this problem in a way only Google could. They tried everything. So you don't have that kind of computational capacity if you're not Google. What they did was they found out a couple of activation functions. They found out a couple of binary operands, and then they combined those together. And they tried that on every data set that is available to them for something like 1,000 approaches. And that's not something, again, that you can do if you are on limited budget. So that's why I am calling Swish the brute force way to life. By the way, for those of you who don't know about it, Swish is x into sigmoid of x. The beauty of it is that was already published a couple of years ago, but nobody found that about that. It's called sigmoid weighted linear unit. And Google just republished that with another aspect added, that is multiplying it by constant beta. So what ARiA is, there is a really famous curve in biology or growth phenomenon, which is called Wish's curve. The curve is kind of complex. It has something like 6 parameters. You can see that on screen. A plus A minus A divided by C plus Q, E raised to minus beta T, then divided by V. Now nobody is going to compute all that. Because in a, say, 100-layer neural network, you have to calculate activation something like at least 100 times. And that's for one epoch. You have to calculate it again and again. And things tend to get slower as you add more complexity to it. So that's not something that you would like to do. And I promised you that it would be a couple of lines, not a paragraph, that you would need to add to your model. Value and switch can be considered special cases of Richard's curve in a way. So now we are going to go from parameter to parameter of Richard's curve and how it affects both Richard's curve and when it's multiplied by the raw pre-activation. So the first parameter is C. So as you can see, if I change the C value to something more than 1, then what I get is the upper bound of the S curve gets increased to that specific value. If I decrease the C value, then that bound gets lowered to that value. But the rest of the curve is unaffected. It still intersects the negative x-axis at the same point. Now, in machine learning, most of the weights of any neural network lie between a specific region that we call region of significance. That's somewhere between -5 to 5. And that's one of the reasons that most of the PyTorch or TensorFlow libraries have half precision arithmetic, because we don't need to store large numbers. We just need that finite precision. So if you multiply the Richard's curve with different C, then what you get is the corresponding ARiA curve. You can see that, just imagine that there is an identity line or line crossing at 45 degrees passing through the origin from this side. And what you have to do is you have to multiply that corresponding point to corresponding point on the Richard's curve. So it divides the total area into 4 parts. The first part is negative large, second part is negative low, the third part is positive small, and positive large. You can see that Richard's curve, in Richard's curve, each parameter affects the outcome in a different way. So if we consider C, the negative part remains as is, whereas the positive large and positive small parts get scaled to that value. Next comes Q. So what Q does is, it has the same upper bound, it has the same lower bound, and it changes the value at which it intersects y-axis. So what that means is, it's going to have the same exact value in the positive region, positive large region, as well as negative large region, but it changes in the region of significance. Next two parameters are a little bit complex because they don't change the behavior of curve individually, but in collaboration. That is K and A. If you can see, if K is equal to 1 and A is equal to 0, what we have is sigmoid itself. Whereas if we change it to 2 and 0, what we have is K sigmoid. But if we switch it to 1 and -1, then we get tan. And that changes the curve ARiA in a variety of ways. The next one is what the authors of Switch put forward. It's beta. And it definitely affects the curve mostly in the region of significance. What it does is it pulls down the curve if that value of beta is lower, and it pulls it up if it's larger. And this is where my initial inspiration lies, because if a curve that is an S curve work for into X, then the same curve should work. So this has the opposite behavior in the negative part, but similar behavior in the positive part, as the beta has. So one of the tricks that I learned in deep learning is it's kind of hard to imagine what's going on through the neural net, so you just don't do it. What you do is you imagine a single hidden layer neural network, you find what effect it has there, and then you compound that effect over and over in your mind to guess what effect it's going to have. So for ReLU, what you can imagine is, since the negative part is 0 and the positive part is itself, what you can think is that it corresponds to the presence of the feature. So if something is there in the image, then ReLU gives you the same output. But however, if something is not there, then it just doesn't care. So what ReLU is, it's kind of like a detector. And that's why most of the people think that CNNs are if the presence of detectors. The first layer of CNNs corresponds to edges, then more complex shape in the second layer, and more complex shapes in the progressive layer. That's because most of the things are trained with ReLU. If you use something different, that behavior is going to change. So if you were to use, say, L, that means that you are going weight to the negative part as well. And what that means is you're not just caring about presence of a feature, but you are also caring about absence of something. Now, that can easily get complicated because neural nets train over time, and you kind of have that ability to pull things to positive region and care about the features that are present more. If you care about both absences and presences, then that kind of gets hard because there are like thousands of things absent from an image, whereas only a few things are present. So you have to care a little about the negative part, but you have to care a larger amount about the positive part. So why do I call ARiA as a family of activations instead of an activation function? Because if you change each parameter, the behavior of curve is altered significantly. ReLU family of activations is a simple combination of any two nonlinearities, and they are pieced together. So what the disadvantage of using any ReLU-related activation function is that there is a if or else loop present. And through backpropagation, that kinds of add computational complexity. Now you would think that this function is complex in itself. So why would I need that? Turns out that it has exact amount of complexity as ReLU or LU because of the lack of if-else loop. And I have timed it over hundreds of epochs, and I have timed it over different data sets. And I have been able to get better results at something approximately 20 microseconds difference. So it's pretty good. So this is what it looks like, but that's not what I said initially. I wanted you to have the same amount of accuracy or more using a couple of lines. But this is something like a parallel. Turns out there are only two parameters which need to be tuned to get better accuracy. That's beta and alpha. And what I call alpha is 1 divided by b. Because what I want to have is a lower amount of negative weights and lower amount of positive weights. Because that's the behavior that is different from beta. Another thing that you can think of is it's acting as a regularizer. So if you pull down the effect of any weight altogether, what that is corresponding to is regularizing the neural net itself. Because what are regularizers? They bring the weights down. if you just switch to 2-parameter versions of ARiA, then it gets shortened to this. That's significantly less than what we initially wrote. And much simpler to write because it's a function of sigmoid. Through experimentation, we found that beta is not the most effective hyperparameter at all. It's alpha. And what I can recommend is you need to have value of alpha exactly equal to 1.5 or around it to get a better accuracy than lane. And this is the version. And that's just multiplying sigmoid or raising sigmoid by alpha value itself. That's pretty easy. And with that, I end my presentation. So if you need to add ARiA to your neural network, you can just add these two lines, and it can give you something like 3% more accuracy.
Thank you, Narendra. Thank you very much. Good, good, good. Hey, that was all the prepared speech for today. Now it's time for the unprepared one, or the time for the more social gatherings and activities. We're all here for that. There's no rush, nowhere. Let's have a good evening, and thanks for everybody to joining up. Thank you. Special thanks to the FX guy.